Hi, everyone. Um, I'm going to cover the solutions to Homework 7 as a video because there's a lot of things I want to talk about um, that are just easier to talk about if we do it as kind of this hybrid idea. Um, so Homework 7 is all problems from chapter 11 and chapter 12. But there's a lot of energy of rotation in here and torque. So as we go through it, I'm going to try to highlight different things and show you what the simulation is showing. I figured this would be easiest. So in interactive exercise 11.1, the main takeaway that I wanted you to get from this was, as it shows in the simulation, if I open this up, whenever we have a ball or a solid object like a wheel or a disc, whatever, rolling, that motion is a combination of translation and rotation. So these red arrows in the top picture show the translational motion at different points. Here, this shows the rotational motion at different points. And here it shows a combination of translation and rotation. So if you added the rotation and the translation together at the top, you get double the velocity of the point. Well, double the translational velocity. The point at the center would simply have the translational velocity. There's no rotation about the center. And the point at the bottom, because the rotation vector points backwards while the translation vector points forward, at the bottom where it makes contact with the ground, it is instantaneously zero. The velocity is what I'm talking about. These, because they're a combination of rotation up and translation to the side, end up at some angle, which should be about 45 degrees actually, considering these two vectors are perpendicular. And if you hit play, you can see how it works. That's all good. So just check out that simulation. For the rest of this problem, we're going to use the information provided at the bottom of the top box. And that's that we have a object, which is a bowling ball, with a radius of 10.9 centimeters. And the speed, the translational speed of its center of mass, is 1.5 meters per second. So it asks us to find first the angular speed of the ball at any point. And from what we can see here, what we would have is that we have a simple relationship between V and R and omega when something's rotating. That rotation, or that equation, is called the equation for rolling without slipping. It has to be rolling without slipping in order for the angular acceleration and the linear acceleration to be the same. If not, if it were sliding at the bottom, this relationship wouldn't be true. If we were to integrate this up, we could get this. We also have that the arc length is equal to the change in angle. We've gone over that in lecture a bunch of times. But what we want here is we want to find omega. So omega is V over R. And remember your units. So V is given as 1.5 meters per second. We therefore need R to be in meters. 10 centimeters is 0.109, 10.9 centimeters is 0.109 meters. And if I divide that, what I get is I get 1.5 divided by 0.109 is 13.76 rad per second. The units are rads per second, and this is about 13.8. Now, question 2 asks us, what is the linear speed at the top of the rolling, or of a point at the top of the ball? We know that that's just 2 times v. It's double the translational motion of the center of mass, which is 2 times 1.5, 3 meters per second. And then finally, it asks us for a point at either edge. And here, we're just going backwards. And what we're demonstrating here is that for a point on the edge, we need to find the actual true v. And we know that this would be a combination of v down, which is 1.5, and a combination of, v translation, which is 1.5 meters per second, and a combination of v down, which is equal to r omega, okay? So from that, we know that this, if we multiply 0.109 times 0.109 times our 13.8, which we already know should give us 1.5, but just as a check, it's 0.1.5. This should be 1.5 meters per second, but this is in the negative y hat direction. This is in the positive x hat direction. So our v is really vx squared plus vy squared, or 1.5 squared plus 1.5 squared, which is equal to 2 times 1.5 times 1.5. Square root of this answer is 2.12 meters per second. We know that if arctan of vy over vx, if these are 1, then this is going to be 45 degrees, but it's going to be negative. And we can see that from the picture. If we really go back to the simulation, what we're looking at here, if it'll open, is we're looking at this velocity right here, which is a combination of the rotation velocity and the translation velocity at that point. Simple enough. I think you guys understand that. This question is really just to make sure that you understand the difference between translation and rotation and how they work together to give you the total motion of a rotating object. All right, so let's move on. Now, this problem is one of those fun problems where we're going to use energy for the first half and projectile motion for the second. There were a few examples of this in Homework 6, I believe, or Homework 5 or 4, where you had the skier going down and jumping off a ramp and all that good stuff. There's a few little things, mostly the way it's set up by Wiley Plus. So we're going to talk about it, and then we're going to talk about how to solve it for Wiley Plus. So let's just first talk about the motion from when it starts at the top to when it reaches the bottom of the ramp. Okay. And note here that this is the first thing. This height is h, but this height is big H. So we're talking about how when it moves from A to B before it launches off the ramp. And we know that it's rotating. It's a rotating object. So we write the energy at A has to be mgha plus mva squared over 2 plus I omega A squared over 2. This is the potential energy of gravity, the translational kinetic energy, the rotational kinetic energy. And now at EB, all we have to do is write the same thing, just changing our variables to what they should be. All right, now first of all, what we need to do is write down what our variables are. HA, HB, VA, VB, omega A, omega B, okay? Note that the height at HA is actually H minus little h, okay? And the height at B is H, right? Yeah, okay. So another thing that I could do, that's not actually true. I'm getting ahead of myself. The height at H is A. Height at A is H. The height at B is little h. That's what I wanted. You'll see I'm getting ahead of myself trying to do something. It starts from rest. It tells us that roll smoothly from rest. So this is initially 0 and this is initially 0. It's not rotating, it's not translating, it's not moving. So we know that these two terms are going to be 0. And now we have one last thing. We don't know what this is, but we need to find this. And we know that there's a relationship between V and R omega if it's rolling without slipping. So this is VB over R. And from that, if we set EA equal to EB, what we get is as follows. We get mg h, remember that this is h at A, okay, is equal to mg h, which is the height at B, plus m VB squared over 2, plus I, and instead of omega B, I'm going to write VB squared over R squared over 2, okay? So we see from here that we get mg h minus h is equal to m over 2 plus I over 2 R squared times V squared. And therefore, we can find, we're going to try to solve this for I. So we get mg h minus h. I'm going to pull a 2, multiply both sides by a 2, divide through by V squared. This will equal, if I do that, m plus I over R squared. So I'm going to subtract m. And what I get is I over R squared. Now here's a key point that I need to tell you, and that's that they're going to consider I, at the very bottom here, they tell you that I is beta m R squared. That is the value of I over R squared. And now what I want to do is I want to get rid of all the m's, and I want to cancel these two R squareds. And so what I get is I get that beta is 2g h minus h over V squared minus 1, okay? That right there is what I need to solve to find beta. Now, how do I find V squared? And I'm going to do this really fast right here. No, I'll do it on the next page. Imagine you have a projectile motion that starts with V of x and V of y, where this is 0 and this is V. And it follows a distance d that we're told in the problem is 0.472 meters. So we need to know what V is in terms of the given variables, okay? We know that x is equal to V times t, V of x, right? And that's what we're trying to solve for, but we don't know t. And we can use that y final minus y initial is equal to V naught of y times t minus gt squared over 2 to find this t. Noting that there's no y velocity here as it jumps off this ramp, and that y final will be 0 and y initial will be h, I get minus h is minus g over 2 times t squared, or t is going to be 2h over g. And so I can solve this equation for v, noting that x is actually d. So I get that v is t over d, I'm sorry, d over t. Okay, and that is, and this should be square rooted, there was t squared. So that is, if I square this, this is d squared over 2h over g, or v squared is g times d squared over 2h. Now looking back at this, I have 2g, so I have beta is 2g h minus h minus 1 over v squared, and this is 2 or gd squared over 2h. So I can see that the g's will cancel, the 2h will come up top, and beta is therefore 4 little h minus h over d squared. And if I plug my numbers in for that, little h is given as 0.11, 4 times 0.11 times big H was given as 0.98 minus 0.11. And then I'm going to divide that whole thing by 0.472 times 0.472. And then don't forget to subtract 1 from it, which I forgot the 1 right here. Don't do that. And what I get is I get 0.71825628482, which is exactly what they got. Remember, your numbers will be different, but the key takeaway here is you can use energy. Energy at the top, energy at the bottom. You need to remember, though, that it is a rolling object, so it has kinetic energy of rotation as it goes down as well. And then projectile motion to find this. Do the projectile motion to find v at the bottom. Use the rolling without slipping condition to turn omega into v, and use that to determine what beta is. It's a little bit of a complicated problem. Once you've done it like twice, though, it's totally easy, and you should understand a lot of things about energy and rotation from this. Okay. Number 17. In this problem, we have the yo-yo. And I gave you this problem because I want to make sure you understand how the yo-yo works. And what's nice about this problem, or not nice about this problem, is really, if they'd given us the units correctly, it would have been super easy and fast. And it is kind of super and easy fast to do. I'm going to explain why this is, but we know that A is G over 1 plus I over R squared. It's negative if it's down. We know this is the yo-yo equation, assuming that a yo-yo starts here and goes down. How we got that equation, though, is imagine that you have a yo-yo that has some tension, okay, and it has its weight, and A is going down. I'm going to forget that negative sign for a minute, and you'll see why. Now the torque, so this yo-yo at its center, there's a tension here, right? And this is R, the yo-yo, and this is the tension of the string in your hand. So there's a torque equation that says R and T, and we can see if we put these tail to tail, that this is going to rotate, R to T is going to rotate positive alpha. So our torque equation, this is a positive torque, and the whole thing's going to rotate. It's going to spin about that direction as it drops. And so what we get here is we get MA is mg minus T. From the torque equation, we get that I alpha is RT. Noting that alpha is A over R, what we get is we get A is R squared T over I, okay? or better yet, that t is IA over r squared. Now, if I go to this and I say MA is mg minus t, but t is IA over r squared, plugging these things in, MA is mg minus IA over r squared, or A times m plus I over r squared is equal to mg, or A is mg over m plus I over r squared, and I think I forgot in this my m. If I multiply through by 1 over m, what I get is I get g over 1 plus I over mr squared. And so whatever I is for the yo-yo, we know that that gives us the acceleration. I chose it to be down. Your book chooses up to be positive. So for me, this is a positive rotation or a positive acceleration down. It's a negative acceleration for your book. I don't like that. I like the acceleration in the direction of motion. Also, we should note that I is mr squared over 2 in general for a disk. So this would give us 1 plus 1/2. However, we need to do this symbolically. So the first thing is, what is the magnitude of the linear acceleration? And if we plug in A is g over 1 plus I over mr squared, we're given the mass in terms of g, or in terms of grams and centimeters. We're given the rotational inertia in terms of 1060 grams centimeters squared. We're given the mass in terms of grams, and we're given r in terms of centimeters. I'm sorry, we're given r in terms of millimeters. So r is 2.78 millimeters. We need to turn that into centimeters, which is 0.278 centimeters. If we put that here squared, we get centimeters squared. And then our units, this whole thing is consistent unit-wise. It actually has no units, and then g is in meters per second squared, which will give us meters per second squared. So what we get here is 9.8 over 1 plus 1060 over 133.278 squared, and that will give us meters per second. If I do this, 1 plus 1060 divided by 133 times 0.7 or 0.278 times 0.278 is 104. 9.8 divided by this answer is 0.09411750031, which is exactly what they got. So this is 0.9094 meters per second squared. Okay. You didn't need to change any units except for the radius had to go to centimeters. Be careful with that. It's one of those Wiley plus things where they try to trick you. Now that we know that, how long does it take to reach the end of the string? As it reaches the end of the string, what are blah, 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 blah? Okay, so we know that it starts from rest. And we know that when it gets to the bottom, it's going to have some V final. First things first, though, we need to figure out the time it takes to get down there. So we can actually go back to our constant acceleration equations and do that y final minus y initial is equal to v naught of y times t. Now, we're assuming that this thing is dropping, right? Therefore, if we measure y initial and y final, if we measure y positive up, our acceleration needs to be negative. If we were to measure it down, we could measure it positive. So what I'm going to do is I'm going to measure it down. So I'm just going to assume that y is positive down, and therefore I get plus a t squared over 2. It started from rest. My y initial will be 0. My y final will be the length of the string. The string is 99 centimeters long. Turn that into meters, 0.99 meters. Okay, my a is the a that I found, and I want to find t. So t is 2 times y final over a square root. And this gives me 2 times 0.99 divided by 0.094. So 2 times 0.99 divided by 0.094. I get 21, take the square root of 21.06, let's say. I get 4.586. Well, I get a little bit bigger number than they got from rounding issues. So I'll just use their time, 4.586 seconds. That's how long it took to fall. Knowing that, I can find its linear speed, its translational kinetic energy, its rotational, and its angular. Really simple. So for part C, we want V final. And we know that V final is equal to V initial plus AT. Multiply this A times this T, you're done. The translational kinetic energy, is, and I'm sorry, I didn't mean to do that. The translational kinetic energy is mv squared over 2. Note that your mass is given in grams, so this needs to be 0.133 kilograms. The conversion is 1,000 grams per kilogram, so 133 grams times 1 kilogram over 1,000 grams gives you the kilograms. Divide by 2, whatever you found for V final, square. That gives you your translational kinetic energy. When it gets to the bottom, remembering that V is equal to R omega, or omega is V over R, we can find the rotational kinetic energy, E, is I omega squared over 2. Now note though, that we've been given I, we were given I as 1060 grams centimeters squared. We need to turn that into kilograms meters per second to get the rotational energy in the proper units to have joules. So there are, in 1 kilogram, 1,000 grams, and in 1 centimeter, or in 1 meter, there are 100 centimeters. You have to do it twice because you're squaring the centimeters. And so what we get is that I is actually 1060 divided by 1,000 times 100 times 100. And I get 1.06 times 10 to the 4. And now the kinetic energy of rotation is I omega squared over 2, which is this 1.06 times 10 to the minus 4 divided by 2 times V final squared over R squared. And remember that your R needs to also be in meters. And your axial radius was given to you as 2.78 millimeters. Make this 0.00278 meters. So when you do that, when you solve all this, my V final would have been 0.094 times 4.5866, so 0.43. Again, there's some issues there with rounding. For D then, what I would get is I would get 1.06 times 10 to the minus 4 over 2 times V final, 0.4317 as they give it, over 0.00278 and square this. So 1.06 divided, well, times 0.5 times 0.4317 times 0.4317 divided by 0.00278 times 0.00278. And then multiplying that by 10 to the minus 4, I get 1.3, which is what they got here, 1.3 joules, okay? And then the final thing is, what is the angular speed? What is omega? And so we can find that from V final is R omega, or omega is V final over R, which all we have to do is we know our V final with 0.431, our R is 0.00278, and you get 155. No big deal. If you understand that, you understand, at least if you understand part C, D, E, and F, you understand the energy of translation and rotation. Okay, all right. Let's go to problem 11. Now these next three problems are actually super simple problems, which is really nice. But problem 11 says a uniform ball rolls smoothly along a floor, then up a ramp inclined at 21 degrees. It momentarily stops at the top of the ramp, and all we need to do is find the initial speed. So these problems, I really should have moved these to the front of this, but it's rolling along, you know, along here. And here, and then at the top, it momentarily stops. So we want the energy at A and the energy at B, and we want to use those to find B. And we're told that this ramp is at 21 degrees, and we're told that this distance was 1.69 meters up the ramp. And we're going to use that to find the finals, the initial speed. So with all of these, what we do is we just write EA and EB. There's no springs in this problem. There's no friction in this problem. So mg h at A plus mv at A squared over 2 is equal to mg h at B mvb squared over 2. And now all we have to do is find h and b for A and B. We're going to assume that when it's at A, it's at 0. I'm sorry. There is rotational motion, okay? And that's going to make things a little bit harder. So we're going to assume at A, the height at A is 0. So height at A is 0. What is the height at B? We need h. So h is equal to d sine of our angle, or 1.69 sine of 21 degrees. And I'm just going to write that down right now. 1.69 sine of 21 is 0.6056. So 0.6056. When it gets to the top here, it's at rest and it's not rotating. However, here, omega, remember, is equal to V over R. So whatever V is, we can do that. And what we have to do now is set EA equal to EB, noting that these go away, and I get mg HB is equal to MBA squared over 2 plus I omega A squared over 2. But I can turn this into something different. Omega A is VA over R. I, for a uniform solid ball, is 2/5 MR squared. And you can look that up. Okay, so let's put this in as 2/5 MR squared times 1/2 times VA squared over R squared. And I'm just going to call it R because it's R of the ball. This cancels, the 2's cancel, and what I get, if I cancel the M's on all sides, what I get here is G H at B is VA squared times 1/2 plus 1/5. This is 5/10, this is 2/10, so this is 7/10. And what I really get is I get VA squared is 10/7 times G times HB. And I already found HB, but we can write it in again. So VA is equal to 10 over 7, square root of 10 over 7 times G times D sine of 21. Right? If I plug in my numbers, 10 over 7 times 9.8 times 1.69 times sine of 21. And then I take the square root of that number, and I get 2.912. And that's it. So I say that's it, but there was quite a bit that we did here. We had to use energy. We had to find the height, V, and omega. And we knew that from the situation that we were told. Then we had to relate omega to V in order to eliminate one of our unknowns. We didn't have enough equations to solve this for two unknowns, right? So we needed another equation, and that other equation is the rolling without slipping, right? So doing that, once we plugged those things in, the only real hard part was to make sure that you knew that the potential energy of gravity, the only thing that matters is the height versus gravity. And we're assuming in this picture that y is up positive and g is down positive or down negative, okay? So once you know that, this is really, really simple. You just set the energy at A equal to the energy at B, make sure that your variables are all in the right form and that you know them, and solve. Not too hard. All right, so let's look at problem 78. Now here is a wheel rolling to a stop. And this problem I assigned to you because I wanted to make sure that you understood the way the forces work on a rolling object, just like on an incline, okay? So this is a wheel that's rolling along with rotational and translational velocity, and it rolls to a stop because there's friction on this floor, okay? And we're told that it rolls into a stop in 227 meters. So we want to know the linear acceleration of this. And you don't even have to overthink this, right? If it's coming to a stop, you can use V final minus V initial squared is equal to minus 2a times x final minus x initial. Why is it minus? Because the acceleration is actually in the opposite direction of our x, right? Solving this for a and noting that V final will be 0, we get V initial squared over 2 times delta x, or x final minus x initial. X final is 227, so x initial we take to be 0, x final we take to be 227 meters. And what we get, because we're told that it had an initial velocity of 39.9 meters per second. So 39.9 squared over 2 times 227. And what I get is, I get 39.9 times 39.9 divided by 2 times 227. And I get 3.5, okay? Which is exactly what they got here. 3.5 meters per second squared. Now I need to know its angular acceleration. And here it's a case of rolling without slipping. So A is equal to R alpha, or alpha is equal to A over R. So just make sure that your radius is in meters. It's 0.362 right here. So if I take that A that I just got and divide by 0.362, I get 9.6868, okay? Finally, if I'm given that I is 2.20 kilogram meter squared, okay? If we want to calculate the magnitude of the torque about the central axis due to friction on the wheel, all we have to do is this A was due to friction. This alpha was due to friction, right? So we know that well, let me actually say it this way. We know that the torque that caused this deceleration was equal to I alpha, right? And therefore, all we have to do is multiply this I by the alpha that we just found. So multiply it by 2, and what do you get? Well, multiply it by 2.2 times 9.686. I get 21.31. And that's it. This is just understanding how torque is related to I alpha. And the thing I liked about this problem is it's a deceleration instead of the normal acceleration that we expect. It's exactly the same, but it's decelerating due to friction. We can look at this as a torque though. And the torque is actually, if the force of friction is acting that way because it's slowing it down, right? So this is our force of friction. It's happening at a distance r from our axis of rotation. Let's draw this torque. R F of friction. If we turn this way, we see that we get a negative alpha. We know that this whole thing is already rotating. It's already rotating that way. So, it's a little weird. This friction I have actually pointed in the wrong direction. And I'll explain that briefly. I'll explain why it's pointed in the wrong direction. So the reason that I accidentally pointed this in the wrong direction is that normally, in order to roll without slipping, there has to be some static friction. But here, this friction force must be going that way. And I know that because R and F have to be slowing down the rotation. R turns to F. This would be a positive alpha or a positive torque. And the whole object, if it's rolling that way, is rolling with omega in the positive direction. It has a net acceleration, angular acceleration of negative, this is negative. So it has a net torque on it of I alpha, which is equal to R force of friction, okay? This is the net torque on it. However, it's initially moving with negative omega. That's a little bit weird, and that's probably why they didn't ask you about it in this. But because it's rotating clockwise initially, and this torque is making that clockwise rotation go away, stop. A better way to see it is, imagine we stood on the other side of this rolling wheel. And so now it's rolling with positive omega, and it's traveling with positive v, and we're assuming that this is the positive direction, okay? So now we see that the force of friction is going to work against the wheel, because as the wheel swings in, the force of friction is trying to stop it. And that's being applied at a distance r. Putting those torques together, our force of friction, we get a negative torque or a negative alpha. And so our net torque on the system is negative I alpha. And that tells us that it's slowing down, if that helps you see it better. There's always a weird issue with rotation of which side you're on and whether things are positive or negative. That's by the right-hand rule that we choose. It just has to stay consistent, but this actually shows you better, I think with the negative sign, what is happening. That the friction that's greater than the static friction that causes rotation alone is actually negative. All right. Moving on. Our final question here is basically what we've done before. It tells us that a solid sphere rolls up an incline. And all we want to know is if it starts at the bottom of an incline and it moves up to the top. Okay. At the bottom, we know that it was moving with v equal to 2 meters per second up. And we know the incline is 37 degrees. It has a weight. We're told the weight, which is mg, is 36 newtons. We may need that to find m. What is the kinetic energy at the bottom of the incline? Now, we know that the kinetic energy at the bottom is actually rotation and translation, okay? We also know it's a solid sphere, so I is 2/5 mr squared. And if we plug this in, we get mv squared over 2, and we also plug in that v is r omega. So omega is v over r plus 2/5 times 1/2 times mr squared times v squared over r squared again. Again, those cancel. And again, we get m v squared over 2 plus m v squared over 5, or 7 over 10 m v squared. Our m is 36 divided by g is equal to m. So our m is 36 divided by 9.81, or 3.67 kilograms. And if we multiply that times 4, so v is 2, so that times 4, times 7 divided by 10 is 10.275. I don't know what they're using for g. So 10.29, let's say, joules. Now, how far will it travel up the incline? Now, we know that at the top of the incline, all this kinetic energy turns into all potential. Kinetic energy and potential energy exchange. At the top, v is equal to 0 and omega is equal to 0. At the bottom, h is equal to 0. So we're assuming that it had mgh at the bottom was 0. It was all kinetic energy here, and here it will be all potential energy of gravity. So this is going to be equal to 7/10 mv squared, right? Or our number, 10.29 joules. Now, we can find how far does it go up, because let's go back to this. mgh is 7/10 mv squared. The answer to the third question is this doesn't depend on mass. H is 7/10 v squared over g, which is 7/10 times 2 squared over 9.81, right? They want to know the distance though, so we're going to have to do one other thing. So 7/10 times 4 divided by 9.8, I get 0.2857 meters. But this is the height, and we were told that it was at 37 degrees, okay? So we know that h is d times sine of 37, and we want d. So d is h over sine of 37, and that's pretty easy to find. Take your h and divide it by sine of 37, and I get 0.47475, which is exactly what they got, okay? It doesn't depend on the sphere's mass. It only depends on the mass distribution, which is actually what I gives you. That 7/10 is because the mass is distributed in a solid sphere equally about the axis of rotation, okay? All well and good. I'm going to actually stop this right now, And then I'm going to come back and we'll do the rest of this homework.